Hello, everyone. My name is Alex Bortak. I'm a lead product manager at Keysight Technologies, and I'm going to present a fabric test methodology that we developed. And I'm going to be using a product called Kai Data Center Builder to execute that methodology. As I mentioned in the previous part of the presentation, I described that product very high level. What the product does, it emulates AI workloads for the purposes of benchmarking the AI infrastructure. And I'm going to be using that product today to walk you through some of the elements of the methodology and showcase how can we improve network performance. The methodology, high level, walks you through a lot of phases you gotta go as you build and as you design and build the fabric for AI to get to the point where it can perform great. The methodology itself is available for everyone for download. At the end of the slide deck, I'm going to have a QR code. Anyone can just download it and read it. So high level, how we approach that. First of all, when you design in a fabric, you have a lot of decisions to make, starting with what kind of topology you're going to use for your fabric. Like, for example, are you going to go with the traditional claw topology, or do you want to have rail optimized topology in your data center? Depending on the topology, you might have different choices about the algorithms you're going to use to move data around, so-called collective operation algorithms. You want to know how those perform depending on the amount of data you want to move. It's a big focus of the methodology itself, and how you slice that data into messages. Then you want to understand that if you have multiple workloads, they don't step on each other, right? They're not creating the noisy neighbor problem. And even within one workload, we actually have multiple communications happening in parallel, right? So it doesn't have to be a neighbor. It can be, you can be hurting yourself. So that's the performance isolation part. Now, load balancing is a super critical aspect of designing the network for AI. And we allow you to compare how different advancements in the load balancing could be compared to each other, right? So if you move from a typical 5-tuple SMP hashing to either using traffic engineering or building the load balancing that's QP aware, or using some other methods, right? So we describe you how to build a test bed, how to set up the test so that you can compare those. And then finally, but almost most important, is how to deal with congestion control, which first comes with question of how to build a lossless fabric. And lossless fabric is being achieved in RoCE v2 and Ethernet using PFC, priority-based flow control. And then on top of that, what are the other methods to control the rate at which the GPUs move data around can be applied, like ECN and DCQCN. And I'm going to actually show you how the DCQCN can be fine-tuned to get the best performance of it. Right? Now, a little bit of terminology that I'm going to be using. So collective operation, let's describe what it is. Collective operation is a way, a software that runs on every single GPU, moves the data around depending on the objective. And there are different types of collective operations, but they all share similar kind of core terms. The first one is rank. Rank identifies a GPU, essentially. So you can have GPU 0, 5, etc. Unique ID. Then the collective size will tell you, well, how many ranks you have in total. Right? You may have 16, 32, 64, and so forth. That's the collective size. On this picture, the size is 4. As you can see, there are 4 GPUs there. And then the data size, what is the data size? It's the amount of data in memory that a single GPU has that it needs to move using that collective operation, right? So That collective operation that I have here is called broadcast. It's asymmetrical. It's one GPU sending the data it has from the memory to everyone else. So in that case, you can think it maybe going to be sending it the same data 3 times. It's a very naive implementation. You could do better, okay? But at the end, this is like the end goal is to get my memory, get the data from my memory, and make sure everyone else has it.
Alex,
that's the broadcast.
Real quickly, sorry for the interruption. Jack Poller from Paradigm Technica. So this collective operation, this is something that typically happens during an AI training, right?
Broadcast typically happens at the very beginning, and then there are other operations depending on what you have.
So this is all in the effort of simulating that particular type of thing that happens all the time in AI.
Exactly.
Okay. Thank you.
Right. Yeah. And then, but most of the collective operations, they are symmetrical. So essentially, every single GPU has the same amount of memory that they need to exchange. And depending what your AI model and workload is, you're going to be using different collective operations. For example, most of the AI workloads traditionally have multiple copies of the model, and they push different data through it in parallel so that the training can finish faster, right? It's called data parallel, and they use all reduced collective operation all the time. Now there are new types of AI workloads that are called mixture of experts. Those types of workloads use all-to-all a lot. Now, if you want to benchmark your network, you actually don't need necessarily to know why one versus another, right? The methodology allows you to make sure that all these collective operations would perform great. And as long as they perform great, you can be sure that whatever workload you're going to throw at the network going to be at least experience certain level of performance. Now, all this terminology is also published by us with this white paper, benchmarking collective operations. Again, downloadable. They're going to be a QR code at the end. And so the second part of the terminology here is what exactly are we measuring? So we're measuring primarily 3 things on a high level. First thing that we measure is how much will it take to complete. It's called collective completion time. And it starts from the very first GPU starting to send data and the very last GPU that's going to finish, right? So if you going to have somebody who is lagging behind, it's going to determine the overall collective completion time. Now, the algorithm bandwidth, it's a metric. It's very simple. You just divide the data size you have by the completion time, and you have the algorithm bandwidth. So I kind of highlighted 2 areas on the slide here that show what happens between the completion time and the algorithm bandwidth. Multiple rows in this table, they demonstrate different data sizes, right? So you start from a very small amount of data, and then you kind of double it, right? And see how the performance changes. So what you might notice is that the completion time area that is surrounded in a red square, doesn't matter that the data size doubles, it stays more or less the same, right? And it's a typical problem with the small data sizes. It's actually not a network that is a bottleneck. It's all the inefficiencies inside the host to start the transmission, to move the data from one buffer to another, and that network is really fast. So like really size of the data size doesn't matter. It's all these inefficiencies that matter. But then at a certain point, you start seeing that, hey, my completion time starts increasing with the data size. And that's where you actually want to start looking into the algorithm bandwidth, but because that's going to describe more like the performance of this collective algorithm independently from the data size at a certain point. Now, there is a third metric here, which actually is being used by everyone. So I described you the 2 basic ones, but really people mostly look at the metric called bus bandwidth. And here is why. So if you imagine two different systems, one has 16 GPUs and another has 32 GPUs. So to move the same data size at every single GPU has between 16 GPUs and 32 GPUs, it's going to take different time. It's just 32 GPUs is going to take more. And for that reason, the algorithm bandwidth is going to be different depending on the size, how many GPUs you have. So it's not very convenient to tell you, well, I was able to achieve that amount of bus bandwidth, because you have to describe how many GPUs I had and everything else. Bus bandwidth removes that from the equation, and it just tells you what was the bottleneck performance in your whole infrastructure. And so that bottleneck really doesn't depend if you had 16, 32, 64, 1000. It just specifies what is the limiting factor that defines how long the collective operation going to take, right? So there was a lot of, I hope, not too heavy terminology, and I needed that so that when I'm going to show you the application and you're going to see some numbers, you at least get certain understanding of what those numbers mean, right? But I'm going to tell you this. So if you're going to get a data sheet or something like a presentation from one of the companies that do AI systems, and they're going to tell you they will be able to achieve that amount of performance, they typically publish a bus bandwidth.
Well, this is actually much better than you just putting the abbreviations up on a slide and having us guess at what they are.
Yeah. Right. All right. Okay. I want to describe what kind of testbed I'm using in this demo, so you get a sense of what it, essentially, what are we testing here. So it is a small fabric made of 4 switches. These are 800 gigs, port speed switches, which I found out run into 400 gig. And I connected my 81 traffic generator to that fabric, so it would pretend to be a bunch of GPUs, right? And so we're going to be testing the performance of that fabric by emulating the GPUs and the network cards, all right? So I'm going to have 16 GPUs/network cards, and the network cards are running, we are emulating, they are running at 400 gig, okay? And I made this fabric lossless, and I will be able to turn on and off the congestion control, and we will see how that impacts performance of the system, the measurements we're going to do. And as you remember, at the very beginning, I showed you the whole sequence of steps in the methodology, and that is like a very end. So think about that. So I already pre-configured everything here in terms of the load balancing, in terms of making it lossless, right? I decided what kind of topology I have. I'm going to run certain types of algorithms, right? And now I'm just focusing on the very end, making sure the congestion control works. So a lot of work been done before.
Just before you go on,
Yep.
CLOS, is that?
Well, it's a Claude topology. It's a French last name, actually. Yes, it just describes this type of network topologies.
It means spine leaf.
Yeah,
Oh.
leaf and spine. Yep.
Thank you.
Okay, so what do you do to make this lossless? You're using like data center bridging, or?
So the lossless, what makes this fabric lossless is the use of PFC, priority-based flow control. And what the priority flow control does, it literally signals to the sender, the one that sends me traffic right now, that I am running out of buffer. And if you don't stop, I'm going to start losing packets because I don't have space to store them. I am congested down the line over there. So that's what PFC does.
Okay, yeah.
Okay.
I am familiar with it. I just wanted to understand, because you said you were going to be turning that on and off.
I'm going to be turning on and off the ECN and DCQCN.
Okay, okay.
PFC will stay on, but we don't want necessarily PFC be the defining factor that guarantees that alleviates congestion.
Yes,
there are reasons you don't want to rely on that always.
We always said that it's not a lossless network; it's a less loss network.
Yeah, you're right. Yes, there is no guarantee that it's lossless. All right. Okay, so let me now switch and show you some of the tour of the product first. All right, so this is the interface, and what I have here, I have a bunch of tests that I did previously. I'm going to open them up and show you the results. All right, so this test, okay, I'll have to hit refresh now. and do this. I'm going to load this test. As you can see, I was running a specific collective operation called all-to-all among 32 GPUs, right? And I did it for a single data size of 1 GB using Rocky V2. Now, if I'm going to go click into the configuration and zoom in into the ECN/DCKCN congestion control, you can see that I wasn't using that capability of the modern network cards to throttle down when they see congestion. And so in this test, I was solidly relying on what we just described, the PFC. Okay, let's take a look at the result that I got. What do I have here? It was a single data size, so I just have a single entry in this table. And it tells me for this gigabyte of data using all-to-all, I got this completion time of 21 milliseconds. You can see this goes really fast, right? And I have these numbers of algorithm at the bus bandwidth. We're actually going to be looking at the ideal percentage. It's just easier for us humans to understand what it is, right? Unless you like remember all the bus bandwidth values that are applicable for 400, 800, etc. So we know what's the theoretical ideal speed of this network could be to run this collective. And so when we measure, we tell you how close you got to this theoretical maximum. So this is actually really good. Remember, I told you I spent time to configure that fabric, right? That's why you have the good number here. Now, even though it's good, I got some number of PFC messages that they kind of highlighted in the red. That means the fabric was pushing back to me and saying, hey, hold on, right? There is congestion from time to time. You gotta like stop, pause. And then I have another indicator here. The fabric was actually signaling me using the ECN, it's explicit congestion notification mechanism. It was signaling me that I have a congestion, throttle down, but I was ignoring it. Remember, I have this enable turned off, right? I was ignoring it. I was kept pushing. And eventually what that led to is the fabric used PFC to say, okay, just stop, right? And go, stop and go, instead of me throttling down or not. So if we look at some details of what happens here. So in this graph, I have a lot of data points. And that's individual pieces of data that I sliced my 1 gigabyte of memory into to send to another 31 GPUs from every other GPU. It's a lot of them here, right? And what I did, I plotted completion time of every single one of them in a line that is sorted. So at the bottom, I have the fastest, and at the top, I have the slowest. And if I zoom in, it kind of, you see, it's not vertical, right? Someone finished sooner, someone finished a little bit longer, but really it is within like 20 milliseconds to 21.5 milliseconds, right? It's a very small range. And the other way to look at that is, like if I'm just going to look at a single GPU, this GPU 0, remember I was saying GPUs have ranks, right? IDs, right? So rank number 0 was sent into other 31 ranks, and they were kind of pretty much finishing around the same time. Like all these lines, they pretty much in the same time around like 21 milliseconds. This is actually quite good and stable. The only thing that you kind of don't like here is that I was ignoring the congestion control notifications signals and instead was relying on the PFC. And sometimes that's not good. Every company and the data center, they make decision for themselves if they want to leave with PFC only or if they want to introduce congestion control. Some people, do not use congestion control at all, but others do. So we want to give a tool to people, for example, like in this case, to see what happens if I enable congestion control, if it's going to have a positive or negative effect. So let's take a look. So in the different test that I ran here, I changed very little. I only enabled the congestion control button, or either checkbox, right? I just enabled congestion control here on every single NIC. Let's take a look at the statistics, what it did. It kind of reduced the amount of congestion I have in the fabric, but the ideal percentage, and I mean, it just dropped, right? So it's I mean, it's horrible right now. So congestion control doesn't help me here. I gotta, you know, I need to do something to do about it. Let's take a look what happens really underneath. So the same chart, it's kind of now, I mean, it's vertical in the middle, but it has two things. First of all, it has some very fast flows that finish within 2 milliseconds. Remember, there was like 21 on average. Now we have somebody who finishes within 2. It means that those guys, they were not congested. Everyone throttled down. These guys were not. They're like, oh, I have all the fabric to myself now. I can finish really fast. Guess what? I don't care because I need the last one, not the first one. And I had everyone pretty much now running around 147 milliseconds. So that's like dramatically worse, right? And some are even longer, right? So, you know, you could think that this is a tail latency on top. In reality, this whole thing is tail latency. I mean, it's just like everything pushed out. All right. So, and I even have a comparison here for you. Completion time between the two examples. Right, so the left, very small. I did not do congestion control, and there is another one, boom. I mean, it's just, I don't know, how 5 times, 7 times? Yeah. And these are the two lines that we were looking at, right? So you see how they are like relative to each other. This is what we had, and we had 97% of theoretical, you know, performance versus this one. All right, so now what can we do? We can actually improve the congestion control by doing fine-tuning of this algorithm. And we are kind of short on time. So what I'm going to do, I'm going to really quickly show you the end result. So this is what the congestion control is supposed to do. When you have congestion notification, you drop, and then you recover. Well, the reality is, this is not a lot of data here. This is AI workload. You finish within 150 milliseconds, you're done. You didn't have time to recover. This was made for storage. This was not made for AI with its default settings. So what you want to do, you want to fine-tune those settings. So you just like squeeze everything so you can recover much faster.
Hello, everyone. Welcome to the DCQC and tuning demo of Keysight AI Data Center Builder. We conducted 4 experiments using different sets of DCQCN parameters, fine-tuning for auto collective in this demo. The DCQCN default configuration here is designed to be conservative in rate adjustment frequency and increments to avoid causing congestion. The DCQCN tuned ramp configuration reduce the interval and the byte counter, aiming to be more responsive to network conditions and increase the rate more quickly. The DCQCN tuned increase step here significantly increase the additive and hyper steps, which are designed to improve network utilization as congestion decrease. The DCQCN tuned final is the most aggressive configuration with the shortest interval and the smallest byte counter, along with the highest additive and hyper increase values. To illustrate the impact of these parameter adjustments, we measure their effects using bus bandwidth, PFC, and ECNC-ERX counter metrics for data size ranging from 128 megabyte to 64 gigabyte with a multiplier of 2. Let's look at the bus bandwidth metrics first. The bus bandwidth of the DCQCN default configuration, represented by the blue line, increase gradually as the data size grows, but at a relatively slow rate. This suggests that the conservative configuration performance is limited and does not fully utilize the network bandwidth. The DC-QCN tuned ramp configuration, represented by the orange line, demonstrates a significant bandwidth advantage when handling larger data size, like 32 and 64 gigabyte. However, it fails to effectively utilize the network bandwidth for smaller data size, like 128 and 56 megabyte. The DC-QCN tuned increased step configuration, represented by the green line, which increase the rate additive and hypersteps, exhibits excellent bandwidth performance. However, look at the PFC and ECNCE metrics, showing a huge number of receiving counters. This may be a side effect of rapidly increasing rate, leading to more congestions. The DC-QCN tuned final configuration, represented by the red line, performs the best among all experiments by decreasing the ramp-up interval and the byte counter further, when keep the higher additive and hyper steps. It also eliminates the PFC and ECNCE counters, indicating excellent network bandwidth utilization. We also conducted an experiment using PFC alone for the same collective data size, disabling this QCN. The plot compares the results of the DC-QCN tuned final experiment with those of the PFC-only scenario. The two approaches are quite close on bus bandwidth. By observing PFC and ECN metrics, the DC-QCN tuned final configuration, represented by the orange line here, shows fewer PFC and ECNCE than the PFC-only configuration represented by the blue line.
Two things. Why do you need a test tool to summarize? First of all these experiments with a test tool is much more repeatable. You can really turn little things and see how they improve. By repeating the experiments over and over, gives you much deeper insights into what's the root cause. You have less equipment, really, and then much faster to run. I mean, it's tool-based for testing.
Just a quick question about the tests that you have. Are you baking in any of the Ultra Ethernet changes into your test tools?
Yeah. So remember, at the very beginning of the previous presentation, I was showing that we can run on servers and we can run on our traffic generators. So the first thing we are already doing is we are working with Ultra Ethernet so that we can run on top of the network cards that are Ultra Ethernet capable. Right, and then we are looking into bringing in the Ultra Ethernet transport into our traffic generators, so we can do both.
Okay, because I mean, this stuff that you've shown would be incredibly useful in actually helping Ultra Ethernet tune their algorithms and their protocols.
Yeah, we are actually a member of the consortium, so.
Yes, yeah, you brought that up. And
Yep. All right. Yeah. So here are all the QR codes for downloads for all the stuff that I demonstrated today.
Are you going to share the slides with the group?
Yeah, I think you actually have them, but yeah.
Okay.
All right. Thank you very much. And the last thing, we're going to have a webinar in a week. Starts April 30th in Americas, and then we go EMEA and the Asia, where we're going to describe that and a lot of other innovations that coming from Keysight in the area of AI.
Okay.